So thank you, and I would like to thank Philip for encouraging me to give this talk here today. And I was a bit reluctant because it's not anything about new applications or new concepts, and it's nothing like that. It arises just from a personal desire to understand the maximum entropy principle better. And but maybe you are interested in see these little calculations that I've done to try to understand the principle better. And it started with, so when I first met, so to speak, the maximum entropy principle, I was really enthusiastic about it because the reasoning behind it is very reasonable, very sensible. And especially the applications and the results were exceptional, especially in statistical mechanics. It really provides a lot of understanding there. But I promised to myself, since the logic behind it was not just rock solid, so I promised myself to explore more later while I was using the principle myself. And in the end, I tried to do exactly that. The point is that I would like to see the principle in a clearer logical form. And there are some questions that you all know about. There is a lot of literature written about this, like, for example, about the expectation equal to average rule that we use as a constraint. Is it valid? Is it not valid? When is it valid? And also, what are the plausibilities? So I will use plausibility instead of probability just to make it different from frequency. So what kind of plausibilities does the maximum entropy rule give? If you look, for example, at the derivation of the maximum entropy principle from probability theory done by Van Kampenhout and Cover in '81, you notice that the results only hold for an event which belongs to the set of data you're used to get your average from. So it's not a new event. But usually, like in statistical mechanics, you use the principle for new events, so for prediction, not sort of retrodiction. And then the usual question, what are the connections between the maximum entropy rule and probability theory or plausibility theory? And you have there also all kinds of discussions and derivation of the principle from plausibility theory or vice versa. So what strikes me is the difference between the logical status of the rule and the logical status of plausibility theory, which can be condensed in one page and in a very clear-cut way. So how do we apply plausibility theory to a real problem? First, we model the problem of interest as a set of propositions connected by some logical connectives, so not, and, or, implies, and so on. Once we have done that, we assign some plausibilities to some of the groups of these propositions, conditional plausibilities. And we can also assign other conditions like equality of some plausibilities, or that one plausibility must be equal, must be greater than another one, for example. And all these assignments must, of course, respect the rules of plausibility theory. And the usual one, the not rule, the and rule, or rule, and the rule for implication. Then once we have done that, we can use these same constraints with some mathematical techniques by, for example, fractional linear programming, to obtain the plausibilities of some propositions that we are interested in, so our predictions. And we can find exact numerical values, for example, or maybe we can just find bounds on these plausibilities. That if we only find bounds, it means we must input more numerical values at the beginning. And that's the big problem of plausibility theory, the assignment of prior probability. And that's where the maximum entropy principle should give a hand. But anyway, and then in the end, if it's a continuum problem, we just take a continuum limit. But here we have all probability theory. And all the theorems like definitive theorem or exchangeability and everything are just particular applications of this, given particular symmetries in the problem. And this is a nice logical form. What you see here, there is also a clear-cut division between the real problem and the theory, because we have an interface between the two where the modeling takes place. So we can have in the real world just a real problem, and it's fuzzy and complicated. And of course, to apply the theory, which is a simplified version of it, we must do some modeling. And this is sort of the soft part. There is not really right or wrong in it. Of course, what we hope to do is to in the theory, to try to grasp at least the most important parts of the real problems. And in the case of plausibility theory, of course, in the real problem, we have facts, hypotheses, meanings, beliefs. In the theory, we just have propositions, connectives, and plausibilities. There are no meanings here, for example. And exactly in the modeling step, that what's important is the choice of the propositions, what kind of connectives to use, and what kind of prior plausibilities to assign. And this is the soft part. So it's not the purpose of plausibility theory to tell us what kind of propositions to use, what initial plausibilities to give, or what kind of connectives to use for the propositions. And one would like to see something like that for a scheme like that for the maximum entropy principle. For example, how could we summarize it in one page? Okay, first of all, what does the maximum entropy principle give us? It gives us the probability distribution for a new event. Or no, maybe it's for an old event, given some proofs of the principles, or some derivations of the principle. And how do we proceed? Okay, we choose a plausibility distribution that maximizes the Shannon entropy. And that's really the sure part of the principle. And then the usual phrase is, take any data into account as constraints for this maximization. This is a bit fuzzy, because that's exactly the same problem that we have in plausibility theory, taking data into account. But how? And typically, we say, okay, if you have prior experiments in your problem, and for example, you have average data, then just impose this average equal to the expectation. And then also the question is, okay, am I authorized to do that in just whatever context, whenever I want, or are there limitations about this rule? And are there any other rules about this constraint average equal to expectation to apply the principle? So starting from, just to answer for myself these questions, I just imagine a very simple experiment. So we have a die, someone throwing a die. We don't know the throwing technique. We haven't inspected the die. The only thing we know is that the die has been thrown n times, and what someone tell us is their average, the average of these n throws. We want to find two things. One, the probability or the plausibility of the result of one of these n throws, and the plausibility of a new throw done with the same technique by the same person, say, and with the same die. And in this problem, I just use as n the particular values, like 2, 6, 12, and tending to infinity, and an average of 5 and of 6. And to answer to solve this problem, I use the maximum entropy rule with the standard expectation equal to average rule, and then plausibility theory with 4 different infinitely exchangeable models. One is the Johnson or Dirichlet model, and the other two is another model that I will show you now. And it's a model which has been discussed by Skilling and by Katica, especially this one, and Rodriguez as well. So I suppose you are familiar with the infinitely exchangeable models. So it's just a part of probability theory in which you say you have a collection of data. If you assume that the probability for this collection of data is independent of any ordering in this collection, so the order doesn't matter, and how many pieces of data we have, then you have that probability for a piece one datum. It can be given by an integral over the probability simplex of the different outcomes each event can have. With a density function, a positive density function defined over the simplex. And we are just taking a sort of the center of mass with weights given by this density function. And when we update this probability, given some knowledge about all data, it is as if we were updating this density function here with the usual Bayes rule. So there is a constant of, there is some constant of, some normalization constant. And this is nothing new. It's just based on update, but it takes this form because of these initial assumptions. And so this is called an exchangeable model. And this particular density defines what kind of model we are using. So if we assume, in addition to those assumptions, that, for example, to assign a plausibility to obtaining 1 on the die, on a throw of the die, if we assume that only knowledge about past frequencies about this phase is important, and knowledge about past frequencies of all the other phases is absolutely irrelevant. Given this assumption, we have that our density function defined in the model takes this particular form. It's the Dirichlet form with a parameter k. It's symmetric in the simplex of probabilities. As k gets larger, this g gets more peaked. It becomes a delta distribution. And indeed, for k very large, this quantity here gets proportional to the exponential of a quantity which is equal to the Berg entropy. Indeed, the contour lines of this function, of this density, are asymptotically equal to the isentropics for the Berg entropy in the probability simplex. In our problem, we use the values k equal to 1 and k equal to 50. K equal to 1, this function becomes the Laplace Bayes uniform distribution over the simplex. So the other model is this one, and I called it multiplicity model because if you see its form, it reminds the multiplicity factor of that tells you in how many ways a given frequency of outcomes can present itself. Here you would have the frequency. But in this case, these are not frequencies. So here we have the plausibility coordinates. And I have no idea what kind of symmetry assumptions could lead to this model. But anyway, let's use it. So this is also symmetric. It becomes a delta distribution as the parameter L gets larger. And its contour lines, as L gets large, are the isentropics for the Shannon entropy, because this quantity, of course, as you know, as you can imagine, becomes proportional to the exponential of the Shannon entropy. In our problem, I use a value of L equal to 1 and L equal to 50. And then I also use the model in which you just say that all throws are statistically independent. And no matter what you know about the past, it must not influence you about your predictions of the future. And you just give 1/6 plausibility to each phase of the die, independently of what you know. The IID model, basically. And so we are saying the data we have is that we know the number of throws, and we know the average in this number of throws. And this is as a precise logical form. So for example, if we know that the average in 2 throws is 5, then we know that the first throw must have given a 4 and the second a 6, or the first a 6 and the second a 4, or both of them are 5. And then given this, so we just decompose in our atomic propositions. And so given this information, we can find this quantity, which is the one by which we update the density of our model. And we can find this quantity with a precise numerical value. And it's the usual factor, so it's the sum is restricted to only to those frequencies that gives exactly this average. Notice that we are not mentioning expectation here. So applying this data to maximum entropy and to the 4 exchangeable models, what do we find? Okay, let's take the first case. let's take, we know that the die has been thrown twice, and we know that the average was 5. Now, what is the probability of obtaining a given phase in one of those 2 throws, past throws, not a new one? If we just blindly apply MaxEnt, we obtain this distribution. But of course, this is wrong, because we know that if the average was 5 and the throws are only 2, none of these 3 phases can have appeared, simply just by summing the phases. So, simply for when n is small, and we are seeking the plausibility for an old throw, maximum entropy is not to be applied, that's for sure. And you see instead our probability theory gives reasonable, not wrong answers. So all the models automatically tells me that the plausibility for 1, 2, or 3 must be 0. And you notice also asymmetry here, which I didn't when I made the calculation, didn't think about, but actually the probability theory gave it to me. And it's just because of the fact that if you have a 4 in one throw, then you have a 6 in the another, so there is the other possibilities that you have a 6 and a 4. So these two plausibilities must be symmetric. And then the question is, what do you find more reasonable of these 4 sets of plausibility distributions? Given 2 throws, knowing the average is 5, I would keep myself more or less giving, supposing that the throwing technique and the die is fair, then just by counting how the outcomes can be, then you would give equal probabilities to all outcomes, because the 5 can appear. You have 3 possible cases, and the 4 can appear twice in those, the 6 can appear twice, and the 5 can appear twice. And that's what the fair model is telling you. And you see these models with the Johnson model and the multiplicity model with L equal to 50 are more or less equal to the fair ones. These ones are a bit too concentrated on the 4 and on the 5, sorry, and I don't like that. So again, 2 old throws, and now we know that the average is 6. And we are asking, what plausibility do we give to a new throw, so a 3rd throw? Of course, if you're applying blindly MaxEnt, it gives, oh no, just give 100% plausibility to the 6. But that's, I find it very silly. Just 2 throws. I don't think that the die is, or the throwing technique, there is some cheating behind it. And so this also I find it, you cannot say it's wrong, but I find it unreasonable, very unreasonable. And the other models are more reasonable, especially these 2 again. Having thrown the die twice and knowing that the average is 6, I will still give a more or less equal plausibility to all other phases. And this reflects this. These again, they give more plausibility to the 6, and I don't find that very reasonable. So these sort of reflect my personal beliefs better than these 2, and absolutely better than the maximum entropy result. And you say, okay, there were only 2 throws. Now, what about 6? If you throw the die 6 times, and you know that the average is 6, which means each of the times the outcome was 6, what kind of plausibility distribution would you give? Maximum-Entropy tells you, just give 100% to 6. The die is, so there is some cheating going on. There is only 6 that can appear. And I find that still unreasonable. Now, the question is, I would like to ask you, so what do you find more reasonable? So what probabilities would you give for a new throw, given this data? A plausibility distribution like this, or a plausibility distribution like this? I mean, you can raise your hands for those who like the 2 at the top. Okay, nice, interesting. And raise your hands, those for the 2 at the bottoms. Okay, I'm also for the one at the bottom, but it's a tricky case with 6. Now let's go. Yeah.
Question. Can you explain what you mean by new throw using MaxEnt?
We have thrown the die 6 times. The average data regards these 6 times, and now they are going to throw the die one more time. So you don't have data about these throws because the data regards the 6 old throws. So what's the probability you give for the outcome of this new throw? That's what I mean by new throw or old throw.
Okay, yeah, I understand that. I was just curious how you use MaxEnt to get the new throw versus the old throw.
Yeah, I just apply it. I have an average, and so I use MaxEnt put in expectation equal to average. Simply. So I must choose a probability distribution. I choose the one which maximizes the Shannon entropy and that has respects this constraint. In this case, this distribution, because it pushes you to the boundary of the plausibility simplex. Simply. Okay, let's keep the average 5 cases. Let's go to 12 throws. So the die has been thrown 12 times, and each of the times you've got a 6. Now, what are your predictions for a new throw? Raise your hands who likes these distributions.
All of them?
So the two on the top. Okay, who likes the 2 on the bottom then? Or prefer the 2 on the bottom? Okay, so most people, I'm also for this one. And so some people that in the previous case chose the 2 lower ones, now they choose the 2 upper ones. That's interesting. So none of these 2 models actually reflects your beliefs properly. A curiosity, notice how all these models have entropy bigger than the maximum entropy result. It's not a paradox because, of course, they discard the average equal to expectation rule. They don't respect that because in this case, or maybe not in this case, but in the past cases, it was not so convincing as a rule to apply. And then finally, let's take the case with a very large number of throws. So n that goes to infinity. And of course, I suppose every one of us would believe that there is some cheating going on. So the dice or the throwing technique are biased, and only 6 can be get. And you see, also probability theory, independently of the model, gives you that answer, like the maximum entropy one.
Excuse me, my understanding of maximum entropy is that you only should apply it when you have a very large population.
It's true. That's my understanding too now. Yeah. But it's not. That's the point. It's not clearly written. If you see about, yeah, that's the point. And there have been some discussions in the past in the literature saying that this. I remember. I think it was an article by Offinker also. So if it can be applied when you must know exactly the number of throws, or you just need to know that n is large, but then large in comparison to what? That's an important question.
Well, it's not 6.
Yeah, exactly, but it depends on the context. But you don't have any rule there to know if n is large or not. A rule of thumbs. So this means that the expectation equal to average rule is not part of MaxEnt. It's part of the interface of how you apply MaxEnt to a real problem. No, I agree with you.
I'm not sure I understand. How did you manage to obtain a 0 probability prediction out of 5 sample with maximum entropy? I'm sure it's possible. I mean, no reasonable theory should predict 0 probability or 1 probability based on Banach number.
Yeah, exactly. I will come to the question later. So if your data, if you know that n is equal to 2, how do you apply that data to MaxEnt? No, suppose I want to apply MaxEnt. I know the average, and I know that the number of throws is 2. I do apply this data to obtain a probability distribution. That's an important question. And I've never seen anywhere explaining how to do that.
Answer. If you use the principle of maximum entropy correctly, which involves appropriate usage of the Kullback-Leibler relative entropy approach, the proper way to use maximum entropy principle to do updating of probability distributions is Bayes' rule. Not this. This is not the way. The reason you're getting wrong answers is because you're applying it wrong.
But you speak about update, but here I want to assign a probability. I don't have any pre-probability to update.
If you do it properly.
No, exactly, but that's the part that interests me.
Equivalent to having validation analysis as you might be doing.
Okay. Okay.
Yeah, so that's what you're proving is actually absolutely correct. If you misuse the principle of maximum entropy by assuming that there is such a thing as a rule, expectations equal averages, you get wrong results. You're right. Yeah. Don't do it.
But the type that we have by Keynes himself.
No, it's an ensemble average.
No, he talked about the next.
James said many correct things and a few incorrect things. And we have to learn to recognize which ones we should abandon and fix.
That's exactly what he's trying to do.
Exactly. But I don't think, I haven't seen anyone doing that kind of...
No, exactly, because you usually apply it to n equal to infinity. That's the point. But if you look in the literature, like tutorials and so on, there is not very much written about this. That's the problem. So this has to be remedied. So you cannot just give this rule which applies just to n equal to infinity.
Oh, absolutely. But shouldn't you use that rule? Idiot.
You can use it in some situation, like this one, for example. It gives reasonable results.
Theorems like that the expected values and average values converge in probability. And those theorems exist, and those are fine.
For probability theory. Yeah, but that's the point again. So we don't have yet the rule in a clear logical form as we have probability theory. And that should be done once and for all. If we know everything, so if we know how to apply the rule in all particular situations, then just put it in a clear logical form. And as you were saying, yeah, when n equal to infinity, then the results given to you for MaxEnt. Okay, let's see this. So an infinite number of throws, and we know the average is 5. This is MaxEnt's answer, which is quite reasonable. If you compare with the other models, you see that, this is the probability for an all throw, so one of the throws contributing to the average. If you see the Johnson model, both for equal the parameter 1 and parameter 50, its results, it looks reasonable, but it's not the same as the maximum entropy one. And you can show that asymptotically, they are not the same. This is an important point. Instead, the multiplicity model gives asymptotically, you can show that it gives exactly the same probabilities as the maximum entropy one. And this is true also for new throws. So for a new throw after all the infinite number of ones which we have done. But again, the Johnson model gives different predictions. I will come back later to this. The first thing that we can see here, okay, so this multiplicity model reproduces the results of maximum entropy model. When this parameter is large, when the number of throws is large, and when the ratio between the two is large. So n must be much larger than L. And it reproduces the same results of the maximum entropy for all the new throws. And this, I think this has been shown in the literature, that these are other models that asymptotically behave like these multiplicity ones. And how does it do that? Of course, because for n large, this part here of the update rule for your exchangeable model selects the average constraint region. And this one, as L goes to infinity, selects the maximum entropy. It becomes a delta distribution on the point with maximum Shannon entropy in that constraint region. So that's how you get it. So nothing special is going on mathematically. And you see, so taking the model with the parameter of 50, and supposing that our die instead of 3 faces, suppose you have data for 5 throws. So this is the curve representing your data. And of course, when this function modulates this one, it more or less takes this one. That's why for a small number of throws, it gives you more or less the equal distribution, which you consider reasonable. Then of course, as the data increase and it concentrates on the average in the region with that particular average, in this case, if it's say 1.5. So the the modulation of one function for the other gives then a peak exactly in this region and in exactly the maximum entropy point. So, what can we get from these calculations? First, that the maximum entropy procedure with average type constraints, you can see that as a limit case of a particular exchangeable model update in plausibility theory. So using maximum entropy in this case, the average kind, means just using plausibility theory with an particular exchangeable model. Second, the maximum entropy method is not meant to be used with whatever kind of average constraints. So you were telling me. So I was using it wrongly. Simply, that's why it gave me unreasonable distributions. If you want to use that rule, then use it for large n's. There is one other thing. Sometimes they say if you get results that are unreasonable or they don't match experiments, there might be additional constraints at work. It's not completely true. The constraints must be the one you know. But the problem is that behind the data, there can be additional assumptions. For example, in the Johnson model, the assumption is if the mechanism producing the data is such that knowledge of the frequency for a given phase is completely irrelevant for predict all other phases, then the Johnson model is the one to apply. It reflects what you know about the problem, not the multiplicity one. And then if you apply it for asymptotically for large n, the right distribution is the Johnson one, not the maximum entropy one. Not because there is an additional constraint, but because there are assumptions in the mechanism producing your data that you must take into account. Maybe you can say that them are constraint if you want, of course. And this, so you saw that you say I can apply this rule when n is large, but when is n large enough? Here we have a sort of degree of subjectivity. As you saw, like raising your hands, some people were already applying MaxEnt almost for n equal to 12, or maybe n equal to 6 was enough. So there is a sort of degree of subjectivity when to apply this rule, when is this rule reasonable. And as you see, so the exchangeable model was more reasonable in the no-limit cases. And you can also show, of course, that all these kind of maximum entropy procedures with average type constraints, with all kinds of entropy, can be obtained in this way with an exchangeable model and a particular density for your model. What the parameter L represents in the multiplicity model is more or less the number of throws that you consider necessary to start to abandon a belief that, for example, in this case, your die and the throwing technique are fair. So you obtain equal probabilities for each one. This is more or less the number of throws to start thinking that, no, there's something going on. And then where also the maximum entropy distribution sets up, more or less. And these are the final questions. So is maximum entropy an up-to-date rule? Personally, I believe not, because we have probability theory for this. And of course, I know that in the literature, so you can derive probability theory from the maximum entropy rule or vice versa. Is maximum entropy with average time constraints an extra plausibility theory method to assign prior plausibilities? No, we saw it's just a limit case of an exchangeable model. And yet, yes, because it selects this particular multiplicity model. And a question which interests me a lot is what kind of symmetry assumptions leads to that model? So we know the assumptions that leads us to the Johnson or Dirichlet model. What are the assumptions that leads to the particular form of the density function for this model? And I know Rodriguez and Katisha have been doing some work about sort of deriving this model using the maximum entropy principle, just speaking with a little bit of hand waving, using the maximum entropy principle on the set of probabilities of probabilities, so to speak. So that's a possible. You can have some research path there to find a mean of this particular model. And the question is, again, so what about maximum entropy used with non-average constraints? Because James himself said, okay, MaxEnt is designed to cover more general situations where it does not make sense to speak of trials. If you have averages, of course you have trials. And personally, I've never seen a sensible example of MaxEnt used with non-average constraints. I've seen examples of MaxEnt used with strange constraints that, though they felt a little bit ad hoc. Of course, you can get to whatever you want with maximum entropy by choosing the right constraints. And the point is that finding sensible kind of non-average constraints. And so this is just at this point my personal understanding of this principle. And this is just some references, some works that have discussed these kind of problems. No, I don't have any. I'm really happy if some of you can show me uses of Max, like for example, Katisha. I'm interested in that. So using MaxEnt with other kinds of constraint, how you do it, and how is the logical setup to do that. So I know what's the theory, how do I model my real problem. So what's part of the MaxEnt principle, what's not?
Well, I have presented many pieces of work over the last 10 years on that theory. I'll be definitely very happy to give you references and we can talk about it.
Perfect.
This coming Thursday, I'm going to give you an example about how proper use of updating techniques using entropy to update can actually help us reproduce quantum mechanics, much in the same way that James reproduced statistical mechanics. So it's like I said in my tutorial the other day, the principle of maximum entropy, like James said, is a very powerful tool. You can build beautiful furniture or you can saw your thumb off. And what you have pinpointed, which is very valuable pedagogically, is a list of ways of not to use the principle of maximum entropy. Which you're right, you shouldn't use it that way. Yeah, you're right. One has to figure out which are the ways to use it that are actually productive.
So the point is that the problem, I immediately knew how to apply probability theory to each of those particular problems immediately. Yes. So just calculations, difficult calculations, so you have to do Monte Carlo techniques, so even for just a 5-dimensional simplex and so on. Fine, but then I get my results, they are very sensible. Maximum entropy, I had no idea. I've been looking at the literature, but really, how do I apply the fact that I know there are 2 throws and the average is 5, for example? Such a simple case.
Of the principle of maximum entropy, not quite MaxEnt with channel entropy. No, not that. The appropriate use will be identical to Bayes' rule.
Okay, then I use the probability theory, basically.
Exactly. Yes, which shows the compatibility of the
Okay, well, that's the point. But we were using MaxEnt to choose. MaxEnt is a complement. So in probability theory, it doesn't tell us how to choose for priors. It should be MaxEnt to tell us what to choose for priors. But then if I'm using probability theory, MaxEnt has no reason to exist. So that's the kind of things I'd like to set clear, because as soon as you say, yeah, but we can do this, but then you're losing the point that you wanted to do the other way for a particular reason. So it's this which is still confused today, or at least I feel still there is a lot of confusion compared to probability theory, which is just, you know where the soft part is, but once you model it, you know how to use it, and it gives you wonderful results. And that's all. Oh.
You just said maximum entropy might have no reason to exist. In fact, there is. Entropy or information is very clearly a variation of potential, telling you how far a particular distribution is a measure or a probability from another one. And that's a valid aim. It's not necessarily intrinsic to probability theory, but it does tell you how to navigate in probabilistic spaces. So it does have a reason to exist.
Yeah, but I think this reason is reflecting the particular multiplicity model. If that gives us...
The multiplicity model has no choice but to get the same answers as maximum-entropy because it's got the same sort of symmetries.
Exactly, but what are the symmetries? That's my question. So how do I derive the particular density function for the multiplicity model from symmetry assumptions, just as I do in the Johnson model? You know, it's the studies of Johnson, and Zabel has published a lot about it. If you make this assumption here, immediately, it's a very simple assumption to make. Immediately, you write it in as a kind of functional equation. Immediately gives you this. So I would like to see a symmetry assumption give you this.
That's the wrong assumption to make for an actual physical value.
Absolutely, absolutely. Each assumption has particular context to be applied. Absolutely. But so what are the assumptions? Since this seems to give reasonable results in a lot of cases, what's the assumption leads me to this? I don't know that. And then some kind of research on this has been made by Rodriguez, I think. Is also you are. Yeah.
I don't know what you refer to in my name in the context of...
Because I'm confused in them. Let's see. No, sorry. I see. Yeah. Let's see. What was it?
Well, since this is,
Maybe it was...
I'd like to ask a question. So can you go back to your old throws with MaxEnt and 2 throws and an average of 5? Can you go to that slide? Please?
Yep. 2 throws and average 5.
So for your MaxEnt solution, my question is, how do you include the information that you have 2 old throws in your MaxEnt?
I don't know. That's my question.
Okay, so you don't.
No.
Okay, so all you have for your information is the fact that you have an average of 5.
Exactly.
You know nothing
And
else.
just applying that is unreasonable, of course.
So, well, so my question is, if you have this information that you have no idea how to include, my problem with the word wrong, when you say it's clearly wrong, I would say it clearly does what it's intended to do, which is if you're using an expectation value that's equal to 5 and you get a certain solution, then that's certainly reasonable based on the information that you're
Exactly.
inputting.
I mean, I said blindly using
Right,
this
but you also
with a
said
constraint.
wrong. And I have a problem with that in the sense that you're applying it, you're using another method where you're putting in different kinds of information, so you should expect.
Exactly. I said if using MaxEnt,
Yeah.
just with the average equal expectation constraint,
Yeah.
to this case, is wrong. The application in this case is wrong. That's not double. That's what you say. Here I have additional constraints that are not taken into account. That's why I get a wrong answer. But nobody has told me how to apply this additional information. That's the point. MaxEnt should be something that helps me to apply data I know, very simple data, to get a reasonable prior. And in this case, it doesn't, because I don't know how to apply this simple data. I find it more easily to apply this with a normal plausibility theory than with MaxEnt. So the roles are suddenly inverted. It should be MaxEnt helping me giving priors for probability theory. So that's exactly my point.
I think all of those are wrong.
Yeah, possibly. You can have another model that reflects more.
I certainly wouldn't bet based on any of those. Right?
You wouldn't do any betting at all. So you don't have you have a personal.
I rolled the dice twice and I got 5 both times.
No, you get an average of 5.
Okay, so I get an average of 5. I'm not going to exclude that on the next row that I'll get a 1.
Sorry, this is for an old throw.
Why do I care about that?
No, so they are asking you. So I throw it twice. What's the probability that in the second of these 2, I got a 1? Of course, if you know the average is 5, you know that there can't have been a 1 in it.
I don't care about that. I usually care about what's going to happen.
Exactly. But so that's why also in this case you get some reasonable conclusions if you apply the maximum entropy principle without taking this into account.
That's why you don't do that.
Exactly, but that's the point. So I'm expecting to use maximum entropy exactly in this case, and instead not. I'm using probability theory. So it's not. I still use maximum entropy, so it's not a critique. The critique is that to the logical condition the principle is it in now today.
You said the result yielded by maximum entropy principle. You said wrong, but that's okay. But can you tell us the exact reason why you like the upper model? Why do you think the result yielded by the upper model is more reasonable than the one yielded by maximum entropy?
And then we go to personal. So my situation is this. Someone has thrown a die, and I don't know the person. I don't know the throwing technique, and I haven't seen the die. I only know this person has thrown the die twice, and I know the average has been 6. Now, if you ask me, what probability do I give for the results of a third throw, a new throw? So it's subjective. Maybe you know that, oh, it's been 6 twice. Surely it's a based die or it's a based throw. If you believe that, that's fine.
That we believe in a solid, it's going to be 6.
Sorry? You believe that, but exactly. But that's the point. I'm not going to this. So each one has a personal belief depending on your past experiences. And fine, absolutely glad with that. And certainly, that's why I asked you, which one do you prefer? If you say you prefer this, if you say you prefer this, actually, for me it's fine. If you prefer that, fine, absolutely. I prefer this, but it's a matter of personal opinion. In this case, I prefer this. I still think, I don't believe that I cannot just because of 2 throws, they're given 6, I believe that die is biased directly. I wouldn't believe that.
Well,
so 2 is too little.
The reasons you give, you like that more, you cannot put that on the basis, on solid basis.
No, absolutely, past experience. You're right.
Like James does, he uses the, what do you call it? Ridiculous, it's most honest part, there is this, when you prefer something goes into it, even if you don't know what it goes.
Exactly. In this case, the soft part which you're speaking about is the choice of model. It means I choose this model. Based on your past experience, you could choose this model, another model, or even something completely different which doesn't rely on exchangeability. And I'm fine with that. There is a soft part, something you cannot say into logical propositions that makes you choose this model, for example, this model one, instead of another model. And you cannot put that into words, or it would be a very complicated, it's your experience with dice, or I agree with that, absolutely. That's why my personal, based on my past experience, which I cannot put in a logical form, I would choose this model.
Principle of indifference.
I don't know what. In this case, when we go to 6, I think we will have more disagreement among us.
Sorry.
Yeah.
Let's thank the speaker.